Thank you so much for the introduction, and thank you to the organizers for having me to talk. The Fields Institute has always been a very special place for me mathematically, in the city of Toronto for me personally, so thank you all so much. As said, I'm Juliette. I'm a postdoc currently at Brown, but that position only lasts officially for another 2 weeks, at which point I'll be starting at Dartmouth. And I'm going to talk about Syzygies beyond projective space, and all of the new work that I'm going to talk about today will be joint with Lauren Cranton-Heller, who is here and who is a postdoc at University of Nebraska-Lincoln, and Marud Serafi, who is a graduate student at Minnesota. And then there is some orientation here between MPI Leipzig and McMaster's about where he will be in the near future. But he'll be somewhere between Germany and Canada. To begin, the story is all about syzygies beyond projective space, but I want to begin by talking about syzygies on projective space. And so what do I mean by syzygies? Well, I mean, throughout this talk, S is going to be the polynomial ring with variables x0 through xn. And just for simplicity, I'm going to work over the complex numbers, although that isn't so important. And M is going to be a finitely generated S module. And then the key definition is that a minimal resolution, I should say a minimal free resolution of M is a complex of free S modules. So you have some complex F0 with maps between it. Let's call the map D0 coming from F1, coming from F2, D1, so a sequence of maps between free modules. And this is just a complex of free modules, and to be a minimal resolution, I have to have some properties. So what are the properties? The first property is that this is, if I put an M here and put this becomes exact. So this complex only potentially has homology at the 0th step, where the homology is exactly M. And step 2, I need to insist on this being as small as physically possible in some sense. And the technical way we can say that is we're going to insist that the image of each map is contained in the maximal ideal, x0 through xn, times the target. So put differently, this minimality condition essentially says that if I fix a basis for each of these, or a generating set for each of my free modules, I can represent these maps as matrices. And this minimality condition is exactly telling me that those matrices are going to have entries that are either 0 or polynomials. They're not going to have any constant terms. And the reason I don't want any constant terms is because if I had a constant term in one of those matrices, we didn't actually need that. We could have split that term off from the complex. That's not entirely obvious, but it's not so hard to check. So this is the definition of a minimal free resolution. And, well, a minimal free resolution is almost synonymous, depending on who you ask, to syzygies. So when we talk about syzygies, what we really are talking about is a minimal free resolution of our module. So when I say the word syzygies, I'm talking about the minimal free resolution. Some people might refer to the syzygies as being the elements in the matrices once you fixed a basis, or they might refer to them as being the kernel of these matrices. All of the same things are analogous, and so I'm going to use the term syzygy somewhat hand-wavily throughout this talk. I have not said it's graded at the moment, but it might be it soon. But as an example, let's do a simple example to see what a resolution actually looks like in practice. So my S is going to be the polynomial ring on 4 variables, x0 through x3. And my module M is going to be the module generated by monomials of degree 3 in 2 variables. So it's the subalgebra generated by s cubed, s squared t, st squared, and t cubed. And you might ask, how do I think about this as an S module? Well, I'm going to think about x0 is acting by multiplication by x cubed, x1 by multiplication by s squared t, and so on. So this naturally makes M an S module. And we could ask, what does the minimal graded free resolution of M look like? Well, I'm going to start with M, and I want something exact here, so I need to surject onto M. And well, luckily, there's a pretty obvious way to surject onto M, hit all of its generators. So we can just surject one copy of S onto M, sending each of my variables to each of these elements. It's almost like I picked those variables so that this map would in fact be surjective. But of course, now I have a nasty problem where that this map, while it is surjective, has some kernel, right? There's going to be some relations amongst these variables, right? So for example, s cubed is equal to, if I square that, that's going to be the same as, nope, that was not what I wanted to do. If I do s cubed and I multiply it by, oh yeah, first and last one minus middle two, thank you, minus middle two, right? This is going to be equal to 0, and so this is an example of a relation that would translate to being x0, x3 minus x1, x2 has to be 0 in this in this kernel. And we could go through and write down everything on the kernel, and we could then figure out what that is. And it turns out the kernel is going to be generated by 3 elements, namely x0, x2 minus x1 squared, x0, x1, x2 minus x0, x3, and x1, x3 minus x2 squared. So it turns out these 3 elements will generate the kernel, and so we get a nice surjective map onto the kernel if we take 3 copies of this. And then you could play the same game. There's going to be some relations amongst these entries, and so we'd get another matrix here. And this is going to be 2 copies of S here. And this is going to be x3, x2, x2, x1, x1, x0, assuming I have my notation correctly. And you could check that if you multiply these 2 matrices together, you definitely get 0, telling me that this is a complex. All of the entries are polynomials, so it definitely satisfies the second condition. And exactness is a little bit more of a pain, but you could check that it's not just a complex, but is in fact exact, as I've written. And it's essentially exact because of how I constructed it, right? I surjected onto the kernel at each step. And this maybe even suggests an algorithm for how you would construct a minimal free resolution. You just kind of pick generators, surject, find the relations, surject. And that's in fact how this goes about, right? We're always can just kind of construct things and take relations on relations on relations. So that's an example, and as was suggested by someone, I don't remember who, I apologize. I've not said anything about my module, but this is a talk that's in some ways about projective n space, and so I really want to have a grading here, which means is because I really want to have geometry present in my life. Life is much better when you have both geometry and algebra. And so what is the dictionary I want here? Well, I'm sure many of you are very familiar with the dictionary, but just to set it up so we're all on the same page, on the geometry side, we're going to have projective n space, which we can think about as being n plus 1 tuples, x0 through xn, modulo the relation that we identify points that differ by a non-zero scalar. So if lambda is some element in C star. Right, so this is projective space, and on the other side, well, we have the ring S, and this is the algebra world on the other side. We have the ring S, which is, as always, the polynomial ring on n plus 1 variables, n plus 1, because those are essentially my coordinates here. But the fact that I have a group action that I'm quotienting out by on projective space means this ring is endowed with not just kind of a ring, but also a grading. So I have the notion of a degree. So this has a z grading, which just tells me that the degree of each variable xi is equal to 1. And this is just telling me how this torus is acting on my big complex vector space. And you might be thinking, Juliette, of course these variables have degree 1. I've done high school math. Every variable has degree 1. I passed algebra 2. And I'll tell you later on, we're going to change this, and there's good reason why. So this might be the dictionary you have, but this dictionary, of course, as we all know, goes much deeper, right? So for example, here, there's kind of a distinguished set, which is maybe the fixed locus of this action, right? F, which is the fixed locus, is exactly when all of my coordinates vanish, is exactly the fixed point of this action. And that's maybe an important thing to keep track of. If we're looking at a quotient, the fixed points are important. And this maybe corresponds to the maximal ideal, which I'll call B, and is x0 through xn. And of course, this correspondence then globalizes in a beautiful, fantastic way. Namely, if I have a subvariety x inside of Pn, I get some ideal Ix inside of S, and more generally, if I have some coherent sheaf F on Pn, I get some nice graded module M. So when I write I here and M, I mean a finitely generated graded or homogeneous ideal or module. I should probably say I'm always going to assume that these two things are the saturated ones. I'm picking them nicely. But we have a lovely dictionary between geometry and algebra. And this is great because now if I gave you something coming from geometry, we could pass to a module and ask, what does its minimal resolution look like? And the name of the game is to ask the question, how does the geometry affect the shape of the minimal free resolution? So what do I mean by shape? Well, I mean kind of 4 things, and maybe only 2 of them have to do with shape, but I'm going to tell some lies, and this is the first one. So by shape, I mean, do these things actually exist? I haven't told you anything about existence. I haven't told you anything about uniqueness, and maybe existence and uniqueness is a type of shape, you know, whether or not something exists is maybe something about shape. The next thing I care about is how long is this, right? If I give you something from geometry, how can you tell me how many terms, how many arrows there are going to be in the minimal resolution? Can we do that in terms of geometry? And the second thing the fourth thing you might want to know about the shape of these resolutions is how wide are they? How tall or spread out are they? By which I mean kind of how many summands occur at each term, right? So this is kind of, you know, we have 1 copy of S, then 3, then 2. Is there a way to keep track of how wide things are going to be? And so those are maybe the 4 questions we want to answer when it comes to how does the geometry affect the shape of minimal resolutions? Okay. And of course, the first answer is yes, minimal resolutions exist. And this maybe even predates some of this dictionary I've written down here. In particular, in 1890, Hilbert showed that minimal, I'm going to put the word graded here, it's not certainly necessary, minimal graded free resolutions exist, are unique. And by unique, I mean up to isomorphism of chain complex. And so this is pretty good. He answered the first question, they exist. He answered the second question, they're unique. And he's actually going to answer the third question. And the length of them is bounded above by the dimension of projective space, which in this case is just n. So we know exactly how long is, if something comes from geometry, its length is exactly bounded by the dimension of the space it lives on, the dimension of the projective space it lives on at least. And so, great, short talk, Hilbert answers 3 of the 4. I have 1 left. That shouldn't be so hard. But it turns out controlling the width of a resolution is much harder than controlling the length. This existence, uniqueness, and length proof, in some sense, comes down to this sort of argument. The existence is you follow this algorithm. The uniqueness is you say, suppose you had two different things. Well, it turns out Nakayama's lemma is going to tell you they're the same. And the length is a little bit trickier, but essentially you construct one resolution for a special thing and show you get everything else from that. So this is actually not so bad. But how do we talk about the length or the width of a resolution? Well, it turns out we have to jump forward from 1890 to 1966. Oh, sorry, question.
This inequality is
Yeah.
easy to understand when it is sharp and
Ooh.
by
When is it sharp and by how much? So that's a great question, and the answer is this inequality is in general sharp in the sense that there are things that achieve that maximum. If you're asking what is the length of a resolution, that is a really subtle question. There are some things we can say. So for example, you might try, if I had something coming from geometry, maybe you want it to be the codimension of the support, and that's true if we're Cohen-Macaulay. But in general, beyond that, that's a very difficult question, and there's a lot of amazing work from people like Rob Lazarsfeld and Claire Voisin and Mark Green kind of connecting into some of those ideas. But it's a fabulous question. Okay, so jumping forward from 1890 to 1966, I'm sorry, but I have to put up a scary definition, or what I find to be a scary definition, which is, it turns out that if we want to control the width of a resolution, so how many terms are there, and even more precisely, what are the degrees of the polynomials that appear in the matrices in this resolution, we need the following definition that I'll attribute to Mumford, although he attributes it, I think, to Castelnuovo, at least that's my understanding of this literature, which is that if we have some integer d, we say a sheaf f is d regular if and only if the higher cohomology groups of f twisted by d minus I, where I is the index of the cohomology group I'm taking, vanish for all I greater than 0, right? So all the higher cohomology groups vanish. Mumford wanted this because he was interested in constructing moduli spaces, like the moduli space of curves that Hannah told us so much about. And it turns out this definition is exactly the sort of thing you need to get things like global generation, and then to get Hilbert schemes and quote schemes and moduli spaces to exist. So this is really why he wanted it, because it allowed him to do beautiful geometric constructions. But it turns out that it secretly also answers the question of how wide, so how many, what are the degrees of the things that appear in these matrices, which at least is some notion of how wide can this be. And that takes the form of a theorem another 20 years into the future by Eisenbud and Godot, which says the following are equivalent. First off, f is d-regular in this definition of Mumford. So the higher cohomology groups vanish in some kind of complicated twist region. Secondly, the degrees of the syzygies are bounded above by d. And I put this in quotes because this is not quite true, but it's morally true. And I told you I would lie to you, so here's a lie. And the third point is that if we take the module M and we truncate it at d, so I take the submodule generated by all elements of degree d or greater, so I take this module here and I resolve it, it has a minimal graded free resolution. The minimal resolution is linear, by which I mean when you write down the matrices for this resolution, every entry in every matrix is either 0 or a linear form. So it's a really strong condition. It's in some sense the nicest sort of resolution you could have. So stepping back, what this says is it says Mumford's complicated cohomological definition is exactly capturing the degrees of syzygies in a resolution. So put differently, minimal resolutions are capturing something nuanced about the vanishing of higher cohomology groups, which is entirely non-obvious to kind of the definition or to Hilbert's theorem when he introduced them, or flash even beyond that to kind of, I think the first person to notice this connection to higher cohomology was Sayre in the 1950s when he was introducing things like the Hilbert function and Hilbert polynomial. Okay, yeah. Yeah, so that's a great question. And I'm being cagey. F is always going to be a coherent sheaf, and M is the corresponding module of sections. So I'm going to take gamma star of F, by which I mean the direct sum of H0 over all twists of F. Yes, that's where we're going next. So that's a great question, right? So if I look here, I look at the entries of this matrix, and well, these are all degree 2. These are all degree 1. So we might think, well, it has to be 2 based on what I said, but this is where the in quotes comes from, because it turns out this is 1 regular, because we have to count degree taking into account the step I am in my resolution. And this is the first step. So I do 2 minus 1, that's 1. This is also going to be smaller than 1, so we get 1. So this is 1 regular. And this is great, because those who know, this is the twisted cubic sitting inside of P3, which is a nice Cohen-Macaulay thing. And so you have everything you might expect. The resolution is length of the codimension. The regular, it's 1 regular, so it's very lovely. Great question. Other questions at this moment?
Why should 1 regular be understood as very lovely?
Because it's almost, so the best that I could have is that these entries were linear forms. And this is the next best thing in that they're either linear forms or quadratics. And since I have something in P3 that's non-degenerate, I definitely have to have things that are degree 2. So being 1 regular is the most you can hope for a curve, a non-degenerate curve in projective space.
F is the structure sheet of a closed degree D hypersurface.
Yes.
Will it be
D regular.
if it's dimension D?
If it's dimension D, yes.
Oh. But if it has singularities.
If it has singularities, it might not be. There's some
If you're D regular, then you're D plus.
1 regular. So like, it's closed under addition. It goes up. Yeah. Other questions? These are fabulous questions. And so I want to claim that this theorem, these 2 theorems, namely the one that I've now covered by moving this board, but Hilbert's theorem on the existence, uniqueness, and length, and Eisenbud and Godot on kind of bounding the width in terms of regularity, give us a rough outline on the structure of minimal free resolutions on projective space. This kind of is the jumping off point. You can go much deeper and ask things about specific varieties, right? You could ask, if X is a canonical curve, what could you say about your variety? Or if X is the projective plane embedded by a Veronese of high degree, what can you say? And these are all amazing questions that have beautiful answers. But at the high level, this is where we want to stay, that the resolution, that when we talk about the shape, we want to have something where the cohomology controls the degrees and vice versa. We have a length bounded by the dimension, things exist and things are unique. And so this ends the part of syzygies on Pn, and we're going to move from Pn to other places. And where are the other places? Yes. Yeah, so I'm claiming that this is in some sense the depth. What are the degrees? Which isn't going to tell you how many things appear, right? That is even a more subtle question. So maybe when I talk about depth, I mean kind of what's the largest possible degree, not so much not the number of generators. Knowing the number of generators is a fabulous question, and it's even more subtle. Things in that vein go to kind of work of Eisenbud, Buxbaum, and Horrocks, kind of have precise conjectures on saying what certain things look like, and it turns out those are extremely difficult. So, and are open in many cases still, but it's a fabulous question. Okay, other questions about projective space before we leave our old friend behind and discover them in a new light. Okay, so why do we want to leave projective space? Well, many things embed into projective space, but not everything. Many things embed other places. Put differently, there are many different ways to compactify the torus. We've already seen some of this coming up in tropical geometry that we've seen in the talks before, and that's all we want to do, is move to a more broader class of varieties, namely toric varieties, that allow us to have more room and more structure and apply to more situations. So what do I mean by a toric variety? Well, what I mean is I'm going to give you essentially the same dictionary that I just covered up. Namely, we're going to have a geometry column and an algebra column. So let's start with the geometry column. So what is the geometry column? Well, Y is going to be a toric variety. That is not very helpful. I've just given a word you might not know, a letter, so that's not helpful. So what does Y look like? Well, Y is going to look like the quotient of Cn plus 1 without some fixed locus modulo the action of some big torus of dimension r. So we're going to take an n plus 1 dimensional vector space, yank out some set f, and quotient out by some action of a group, a torus C star to the r. And this will be the thing. So you can see maybe how you might get projective space, right? F would be a single point, R would be 1. You could also imagine you get other nice ways to compactify torus. Algebraically, on the algebra side, well, again, always and forever, S is the polynomial ring on n plus 1 generators because our ambient vector space is C to the n plus 1. Now, I have an action of C star to the R. So instead of having a Z grading, I'm going to have a grading. We're going to have a Z to the R grading, which just means there's a way to say the degree of each variable, and that is now an element of Z to the R. And for the experts, right, Z to the R is just some isomorphism with the Picard group of my toric variety Y, if you would like. It's essentially keeping track of the line bundles or the way the torus is acting. F here is going to be the fixed locus of my action. And this is going to correspond to some ideal B that we call the irrelevant ideal, because things on it are things we don't care about because we're yanking it out. Just like when we're doing projective geometry, we don't care about so many things that vanish on the maximal ideal. We throw those away. So this is the kind of the standard dictionary, and then again, it globalizes. If you have a subvariety X inside of your toric variety, this corresponds to an ideal I sub X inside of S, but now it's a Z to the R homogeneous ideal. And if you take a coherent sheaf F on Y, that corresponds to some nice Z to the R graded module over S. So you have the same exact dictionary between algebra and geometry that we had before. The only difference is that the grading is different and the irrelevant ideal could be different. And we'll give you a concrete example in a moment. I'll note that I should really maybe attribute this to David Cox, who kind of worked out in '95 the correspondence between toric varieties in algebra in this way. Eisenbud, Mistata, and Stillman also contributed to this kind of correspondence between geometry and algebra. This ring S with this grading and this ideal are often known as the Cox ring in honor of David Cox, although he prefers to call it the total homogeneous coordinate ring of your toric variety Y. Okay, so let's do an example to make sure we're all on the same page. And the running example I want to have is P1 cross P2. So something slightly more complicated than projective space, but slightly not too out there. So let's say Y is P1 cross P2. Well, I can think about this as coming from having a two-dimensional torus, C star 2, act on C4 by saying if I have a point x0, x1, y0, y1, y2, this is similar where I can scale my x's by one coordinate, lambda, and then scale my y's by a different number, mu. C5, thank you. I'm good at counting sometimes. All right, so this is the action we have of our torus where lambda acts on the first two coordinates and mu acts on the second two coordinates. All right, so this means our ring S we can maybe easily write down as x0, x1, y0, y1, y2. This has a Z2 grading. And the degree of the x's is exactly going to be my first standard basis vector, and the degree of the y's is going to be the second standard basis vector, essentially because these are acting with powers 1 and these are acting with powers 1 as well. So this is the grading I have on this ring. This is what we'd call the Cox ring of P1 cross P2. The fixed locus, right, F, is when x0 and x1 vanish, or when y0, y1 equals y2 vanish. Right, you kind of have a union of two different irrelevant sets. And this means my irrelevant ideal B is exactly the intersection of my two sets of variables, x0, x1, intersect y0, y1, y2. Okay. And so you see the irrelevant ideal here is some monomial ideal with degree 2 generators. And this would kind of set up the correspondence. And in fact, why might you care about things like P1 cross P2? Well, as I said, sometimes things naturally live in spaces like this. So for example, if you take a hyperelliptic curve, any hyperelliptic curve of genus 4 naturally embeds in P1 cross P2 as a curve of by degree 2, 8, I believe. So we get some curve x living inside of P1 cross P2. And somehow that's a pretty natural place to put a genus 4 hyperelliptic curve if you're interested in studying. Naturally, other things like certain moduli spaces of curves often also live in products of projective space. So toric varieties are a fairly natural next generalization of projective space. And this dictionary means that we get from any geometric object an ideal or a module. So there's some defining ideal to this hyperelliptic curve we could write down. And we could ask, once I have an ideal or a module, we could ask about its minimal graded free resolution. And so what can we say about minimal graded free resolutions? Well, if I take a module M coming from this geometry, it turns out that Hilbert's theorem, although it's not at all phrased like this, applies just as well to this multi-graded setting of working on other toric varieties. And so if M comes from some coherent sheaf on a toric variety Y, then the theorem of Hilbert, again, says minimal resolutions exist. They're still unique. And we get a bound on their length. The length is less than or equal to the dimension of Y. But now we have to fix this. This is wrong in general. And the fix is I have to add the rank of the Picard group of Y minus 1 to get the right bound on the length. And you can see that here in this example, because, for example, this is a polynomial ring with 5 variables. And so you could, in theory, have resolutions over a polynomial ring of 5 variables of length 4. And in fact, you get that. So for example, it turns out that if you take a hyperelliptic genus 4 curve, you can write down the resolution. And here one is. It's very complicated. We don't need to go over what all the details are. But the numbers here just tell you what are the degrees of the matrices with negative signs put in there for some reason. But there's a lot of things. It's very wide. It's also quite long. There's 1, 2, 3, 4. It's a length 4 resolution of something living on a 3-dimensional space. So that's not ideal. Even worse, we might hope that this was short because we want our hyperelliptic curve to maybe be close to Cohen-Macaulay, even if it's not quite there. So this is just a mess. You look at this and you get very, very sad. And you say, this thing is broken. Everything is broken. Existence and uniqueness are good, but the length is too long. It's too fat. It's too wide. There are things we really don't like about this resolution. And this is where we start to think, well, maybe minimal resolutions aren't the right thing on toric varieties. Maybe we want something else. But we say, hold on, let's not jump to conclusions yet. And we say, maybe we can bound the degrees of the generators in terms of some cohomological vanishing. And it turns out that in 2004, Diane McLagan and Greg Smith introduced a notion where they said if we give some vector inside of z to the r, we say that f, a sheaf on a toric variety, is d-regular for this vector if and only if the higher cohomology groups of this sheaf vanish in some way. And I'm going to be very, very cagey about what the vanishing is. Essentially, it needs to be for all twists inside of some region that they define that depend on the cohomology group I and the point we're testing for regularity. So it's some infinite region that you have to check for cohomology vanishing. And it turns out this generalization recovers all the beautiful geometric theorems of Mumford that you would want. So this is the right notion of regularity on a toric variety geometrically. And you might say, okay, does this control the degrees of syzygies? The answer is no. So work of myself, Lauren, and Marud says that there are examples where the degrees of the syzygies do not determine the regularity. There's a relationship, but it is not at all tight like you would want it to be, and so this fails. And at this point, you are very sad, and you say, well, maybe minimal resolutions weren't the thing I should be loving all along. I need something else. I need to fix that these things are too long, that they're too wide. How can I fix this problem? And well, a potential answer comes about in 2017 in the work of Burkesh, Ehrman, and Smith, who say, well, maybe the problem is that this definition of a minimal resolution is too restrictive, right? To be a minimal resolution, we have to have no homology at all. And that's not ideal. Maybe we want to allow a little bit of homology, just a little treat of homology, if you would. And how much homology do we want to allow? Well, maybe we want to invoke something to do with this irrelevant ideal. So what do I mean by that? So the definition that's key now, this is Burkesh, Ehrman Smith, 2017, is that we say a virtual resolution of M, so the virtual resolution of a virtual resolution of a module M is a free complex F dot, so it's a complex of free S modules. I should be saying everything is graded in sight, such that when I sheafify the complex, it resolves the corresponding sheaf associated to M. So I take M, I take the corresponding sheaf, that's some OX module or OY module. I take the corresponding complex of sheaves, that's a complex of line bundles. I need that to be a resolution. So as a complex of modules, I can have homology, but that homology has to be supported on the irrelevant ideal, because once I sheafify, everything that was non-exact needs to disappear, which means geometrically it has to be living on the point we're yanking out. And the idea here is that maybe this is a good analog of minimal resolutions. And I'll note this idea of allowing some sort of homology has appeared in other veins in other areas of mathematics. So Hochster and Hunicke kind of have a notion of allowing a little bit of homology if you want to study things like tight closure. Of course, in almost mathematics, there's kind of a notion of allowing things up to some nilpotency. It's been very useful. So this idea of allowing just the right amount of homology, maybe that's what fixes this. Maybe that's what's going to get rid of this rank of Picard group term and make this correspondence between regularity and degrees of virtual resolutions come up. But you immediately run into a problem, which is, okay, do these things exist? Sure, because minimal resolutions exist. Any minimal resolution satisfies this definition because it is a free complex and it's already exact. So it works. But you could also get other things. So for example, here is a virtual resolution of the hyperelliptic curve of genus 4. But it turns out if I take the subcomplex supported just on these terms I'm coloring in orange, these terms form a virtual resolution as well. That's entirely non-obvious. It's a check you can do with Macaulay too, but it forms a virtual resolution. And maybe you think of that as a good thing because this looks very small. The thing I've colored in orange is short and narrow. So that's good. But this is definitely a different virtual resolution than the long thing. So we've immediately lost uniqueness. Virtual resolutions might exist, they always exist, but they're certainly not unique. So we're in this quandary where we can pick things to be short maybe, we can pick things to exist, we can pick things to be narrow, but we maybe can't pick things to be unique. And in fact, it's not always even clear, can we pick things to be short? So I'll say, we're going to call a virtual resolution short if the length is bounded above by the dimension of my variety, y. So when we talk about short virtual resolutions, we exactly want the analog of Hilbert-Syzygies theorem to work. Yes, question? Yes. If you ask for the minimal length, that's a great question. I don't think it's unique even then. So there exist resolutions of the same length, I think even of this example, so length 3, that wouldn't be exactly the same. And Lauren's shaking Okay, my co-author is backing me up. Yeah, so that's certainly not true. So even if you add a minimality condition to this, it doesn't work. So the non-minimalness is something that's really baked in. And I think maybe what you should be thinking here is, well, maybe the issue is we have to figure out what the right way to represent a module is, right? If I give you a coherent sheaf, what's the right module to represent it? David Cox tells us to pick one that has pretty good properties, but it's algebraically maybe not always the best model. And so how can we fix this? Well, the first thing, I've been babbling about uniqueness, is do short virtual resolutions exist? And well, Burkish, Ehrman, and Smith didn't just give a definition for nothing, right? They actually proved a theorem about it. And what they were able to show is that virtual resolutions exist for products of projective space. So theorem, Burkish, Ehrman, Smith, from 2017 as well. Short virtual resolutions exist when Y is a product of projective space Pn1 cross Pn2 cross Pn to the R. So in this particular case, they exist. That maybe isn't too convincing, but even proving this is non-trivial. So the conjecture that short virtual resolutions always exist from this, but even checking this is non-trivial. So how do they show that short virtual resolutions exist? Well, they do a pretty intense argument where they say, let's take a product of my products. So we take a product of Pn cross a product of Pn, and note that we have two projections now. Pi1 and Pi2, and they essentially use a Fourier-Mukai argument where they take their module M down here that they've sheafified and twisted by an appropriate twist D. They pull it back here by Pi2. They tensor with the resolution of the diagonal that generalizes Balancin's resolution of the diagonal and push forward, and then they argue via spectral sequence argument that somehow the derived push forward of that is going to give you a virtual resolution. So the kind of argument is very complicated. You pull back, tensor, push forward, spectral sequence things, you get a short virtual resolution, and while it's constructive, it's entirely non-computable. At least unless someone in this room is really good at computing Fourier-Mukai transforms on Macaulay 2, you can't ask a computer to do this. It's just kind of a sad part of the theory here is that they exist, but we can't compute them, which is the exact opposite of minimal resolutions, which exist, and we can compute them. So another downside maybe to the theorem. But it turns out virtual resolutions have some good things about them. I've said a lot of bad things maybe about virtual resolutions, like they're not unique, like their existence is not computable, but it turns out we can do some nice things with them. In particular, we get the following result, namely, this is due to myself, Lauren, and Narud, which says, well, how can we actually try to compute these virtual resolutions that Burkish, Ehrman, and Smith constructed? How can we actually construct them? And what we were able to do is we were able to prove that a sheaf F is D-regular if and only if, when we truncate the module at D, this has what we call a D quasi-linear resolution. So the entries in the matrices are controlled in some way that isn't quite linear, but is close. And this implies that M truncated D, the minimal resolution of this, is short. So in particular, if you want to find a short virtual resolution of M, find where it's D-regular, truncate at that spot, and then take a minimal resolution. That minimal resolution is something we can compute with Macaulay 2, and in fact, will be short. So that's great. We now have a way to actually compute short virtual resolutions on products of projective space. It turns out that in the last year, kind of amazing work of a number of authors have shown that virtual resolutions, or short virtual resolutions, always exist. So this was in 2022, and last year in 2023, we get the following result. Originally due to Hanlon's, Hicks, Lazarov, and then later Brown and Ehrman, and around the same time, work of Favreau and Huang kind of show the following. Theorem, Hanlon, Hicks, which is that short virtual resolutions, so virtual resolutions whose length is bounded by the dimension of my space, exist on all smooth projective toric varieties. So kind of before this, we were stuck working on a product of projective space, and this paper blew everything open and allowed us to move to every toric variety. And this paper really is a tour of force. It comes from kind of deep ideas in homological mirror symmetry that construct exceptional collections or nice collections of line bundles in the derived category of a toric variety. And so somehow this is an extremely powerful theorem, saying these short virtual resolutions exist. We're stuck, though, with the last issue, namely short virtual resolutions exist, but they're not unique. How can we fix this uniqueness problem? In some sense, we're stuck with it. Short virtual resolutions might never be unique. But it turns out that if we restrict to not just minimal virtual resolutions, and by minimal, I mean mimicking the same definition as before, right? No units in the matrices, and we restrict the degrees quite a bit, we do get uniqueness amongst virtual resolutions. And this is the theorem I'll end on, which is a bit of a mouthful, but again, due to myself, Lauren, and Rude, and this is not quite on the archive, but we hope to have it there shortly, which is if we say, if we let Y be a smooth projective toric variety, we have to have a condition here, namely that we need E1 through ET to be a full, strong, exceptional collection of honest, God-fearing line bundles. Okay, so if we're on a smooth projective toric variety and we have a collection, a full, strong, exceptional collection of line bundles, which is just a nice collection of line bundles that generate the derived category and have relatively few extensions between them. So if we're in this situation, and if F dot and G dot are virtual resolutions of the same module M, such that when we sheafify each summand that appears in the sheafification of F and the sheafification of G is in E1 through ET, then these virtual resolutions were in fact isomorphic to start with. So virtual resolutions whose summands are in a full strong exceptional collection of line bundles are unique. This seems very restrictive, and it is. But for example,
Is there like summons, like one needs to be in one object and so on, or like?
nope, just every, like these are gonna have, each term of this is a direct sum of line bundles, and we need every line bundle that appears here has to be contained in this collection. Not everyone, not in any order, but they have to all be there. And this is a very strong condition, but for example, every resolution you construct in this way will satisfy that property. So immediately we see that the resolution we construct by truncating at D and taking the minimal graded free resolution is in fact the resolution Burkash, Ehrman, and Smith abstractly compute as a Fourier-Mukai transform. So somehow, even though this is a fairly strong condition, in nature, most of the examples we compute have this property. And so we sometimes can save uniqueness, although this is far from being all of the case. But I think this might be the best we can hope for at the moment, although I'm sure Lauren and Jesse might say more interesting things that hopefully don't contradict what I've said so far. So thank you all for listening, and I'll open it over to questions.